Somebody on Reddit just ran Kimi K3 on 8 gigabytes of RAM. Not a tiny Kimi, not a toy clone, not a distilled model wearing a fake name badge. Kimi K3, the huge one. The model with roughly 2.8 trillion parameters. The model whose checkpoint is about 1.56 terabytes. The model that sounds like it should live behind a wall of expensive GPUs, not inside the memory budget of an old laptop. And the weird part is the claim is real. It ran on one CPU with no GPU, with no COO with no PyTorch, with no giant AI framework hiding the hard part, just a small C99 inference engine, a Linux machine, a lot of storage, and a deeply unreasonable amount of patience. But this is not the normal local AI story, because the headline makes it sound like the hardware wall just got destroyed, and then the numbers come in and quietly rebuild the wall somewhere else. Yes, it ran in 8.24 gigabytes of memory, but one early demo took 261 seconds to generate 8 tokens. That is around half a minute per token. So if you ask it for a medium answer, you may want to make dinner, clean the kitchen, develop a new personality, and then come back. And somehow that is still not the important part. The important part is that this Reddit experiment shows where local AI is actually going, not toward everyone cramming frontier models into cheap gaming laptops tomorrow. Toward something stranger, models so large they no longer fit anywhere normal, hardware that treats memory like a luxury item, and software that starts asking a new question. What if the model does not need to be loaded? What if most of it can stay asleep? What if your SSD becomes part of the inference engine? That is why this story is more interesting than the benchmark, because the benchmark is terrible. The idea behind it is not, hey, don't forget to like and subscribe for more like this. Now, back to the video. The post showed up in our local llama with a title that feels engineered to start an argument. I pushed Kimi K3 onto one CPU with 8 gigabytes of RAM. That is the kind of sentence where every word makes the last word less believable. Kimi K3 is not a normal local model. Moonshot describes it as an open-weight, multimodal, agentic model. It has a 1 million token context window. It is built for long coding sessions, tool use, knowledge work, images, video, and reasoning, and the model card lists the architecture as mixture of experts. Total parameters, 2.8 trillion. Activated parameters, 104 billion. Number of layers, 93. Number of experts, 896. Selected experts per token, 16. That last number is the crack in the wall, because when people hear 2.8 trillion parameters, they imagine the whole model waking up every time you type a prompt. That would be impossible on ordinary hardware. But Kimi K3 does not work like one giant dense block. It is a mixture of experts model. Think of it less like one enormous brain doing every calculation at once, and more like a giant office building where only a few rooms turn the lights on for each token. The building is huge. The power bill for the whole building would be absurd. But for one token, only some rooms are actually active. Kimi K3 has 896 experts. For a token, it selects 16. That does not make the model small. The rest of the weights still exist. They still have to sit somewhere. They still have to be available when the router asks for them, but they do not all have to sit in RAM at the same time. And that is the trick. The Reddit project does not make Kimi K3 magically lightweight. It changes where the weight lives. Instead of saying the whole model must be resident in memory before the first token appears, it streams pieces from disk when needed. The model is not squeezed into 8 gigabytes. The working set is. That difference is the entire story. The project is called Kimi K3 It is a small inference engine written in portable C99. The README makes the positioning very plain, no BLAS, no framework, no GPU, and this matters because it is not just another wrapper around an existing runtime. The whole point is to show very explicitly how the bytes move. Most local AI demos hide that part behind a stack. Ollama hides it, LM Studio hides it, Cloud API-S definitely hide it. That is fine when you just want answers, but if the question is, how can a 1.56 terabytes checkpoint produce text on an 8 gigabytes memory budget, hiding the byte movement is exactly the wrong thing. So this project turns the whole run into a ledger. Start with the nightmare version. If you try to hold 2.8 trillion parameters naively in bfloat 16, you're in multi-terabyte memory territory. The project uses a 5.56 terabytes naive figure. That is not a laptop, that is not a normal workstation, that is a procurement meeting. Then the actual shipped checkpoint is much smaller, around 1.56 terabytes. Still enormous, still bigger than the RAM in almost every machine a developer owns, but smaller because the routed experts ship in a compact 4-bit form. Then the project notices the important split. Some parts of the model are always active. Those are the trunk. Other parts are routed experts. Those are mostly asleep on any given token. The always active trunk is still huge. The project puts it around 113 gigabytes. That alone is already too much for an 8 gigabytes laptop. So the final move is the one that makes the headline possible. Stream the trunk too, pack the dense layers into a 109 gigabytes trunk file, pin whatever fits into RAM, read the rest from disk when the layer is needed. Keep a small cache for routed experts, and accept that your SSD is now part of the model runtime. This is not a normal AI speed optimization, it is almost the opposite. It takes something that should be fast only when everything is in memory, then says, what if we make it painfully slow but possible? That sounds like an insult. It is actually a useful engineering category, because a lot of breakthroughs start as awful versions of something that should not work. The first version proves the door exists, the second version starts caring about whether anyone wants to walk through it. Here's the part that makes the 8 gigabytes claim feel like a magic trick with the curtain pulled back. You do not need a giant GPU, you do not need 500 gigabytes of RAM, but you do need about 1.7 terabytes of free storage. And not just any storage, fast local storage, ideally NVMe. The checkpoint is about 1.56 terabytes. Then the packed trunk adds around 109 gigabytes. So the memory number went down, but the storage requirement became the toll booth. That is why this is not really a story about running Kimi on a cheap laptop. Most cheap laptops do not have 1.7 terabytes of free fast disk lying around, and if they do, the CPU may still make the experience miserable. The official requirements are also narrower than a casual headline suggests. Linux x86 64, VA X2 and FMA on the CPU, no macOS, no Apple Silicon, no Windows path in the current version. And because this is a base model setup, the early demo is not a polished chat assistant either. One captured prompt was, the capital of France is. It produced Paris and then continued like raw model text. That is correct, but it is not the same experience as opening a modern assistant and asking it to refactor a repo. Then there is speed. The README shows an ordinary laptop preset at about 26.5 seconds per token on its measured machine. One early captured run showed 32.69 seconds per token. Either way, this is not interactive. This is the opposite of interactive. This is write a prompt, go live your life, and maybe come back to a sentence. And that is where the story gets easy to mock. Because if someone says, I can run Kimi K3 locally, and the answer comes out 1 token every half minute, the obvious response is, congratulations, you invented a very expensive candle. But the wrong lesson is to laugh and move on. The right lesson is to ask why it works at all. Because every part of this catch points at a real bottleneck. Memory is not the only gate. VRAM is not the only gate. The shape of the model matters, the storage path matters, the cache policy matters, the way experts are packed matters. The reason this is slow is also the reason it is possible, and that is the part local AI people should care about. The easiest way to misunderstand this project is to say, if only 16 experts are active, then the model is basically small. No, that is not what is happening. Only 16 experts are selected per token, but there are 896 possible experts. Across a longer generation, the model may need different experts at different times, so the complete expert set still has to be stored somewhere. You cannot throw it away. You cannot pretend it does not exist. You can only delay when you pay for it. Traditional inference pays up front. Load the model into memory. Keep it hot. Generate tokens. That gives you speed because the weights are nearby, but it gives you a giant minimum hardware requirement. This project pays later. Keep only the working set in RAM. When the router chooses experts, pull the needed expert weights from disk. When the trunk layer is needed, stream the packed layer, then move on. That changes memory from a floor into a dial. More memory does not change the answer, it changes the weight. The project claims byte identical output across memory budgets. That detail matters. It means the smaller run is not using a worse model. It is not dropping layers. It is not sampling from a smaller approximation. It is doing the same math with the same weights, just with a slower path to reach those weights. That is why the result is technically impressive even when the product experience is awful. The model did not get smarter, the laptop did not get stronger. The runtime changed the deal. Instead of asking, can the machine hold the model, it asked, can the machine reach the pieces in time? And once you see that shift, the whole local AI conversation changes a little, because the question stops being only, how much VRAM do I have? It becomes, what is the active working set? How sparse is the model? How predictable is expert routing? How fast is storage? How good is the cache? How much latency can this use case tolerate? For a chat assistant, 30 seconds per token is dead. For a learning artifact, it is fine. For offline batch jobs, maybe a future version of this idea becomes less ridiculous. For long-running agents, the answer depends on whether the work is latency sensitive or just throughput sensitive. That is the real boundary. Some AI work needs a reply now. Some AI work just needs an answer eventually. This project is terrible at now. It is interesting. For eventually, this is where the story becomes useful for developers because local AI has two versions. The fantasy version says, one day you will run the best frontier model on whatever machine you already own. No cloud bill, no rate limits, no privacy concern, no vendor deciding what model you get. Just download the weights and own your intelligence. That is emotionally very appealing. It is also usually where the bad advice starts because the phrase local AI hides too many different things. Running a 4B vision model in 3 gigabytes of RAM is local AI. Running a 30 billion coding model on a gaming GPU is local AI. Running a 2.8 trillion parameter model from 1.7 terabytes of NVMe at half a minute per token is also local AI. Those are not the same category in practice. They only share a slogan. If you're a developer trying to replace Claude Code or Codex for daily work, this Kimi K3 experiment does not solve your problem. It does not give you a snappy local coding agent. It does not make an 8 gigabytes office laptop suddenly competitive with hosted models. It does not mean the GPU market just got bypassed. For normal use, the hosted Kimi API is still faster. A smaller local model is still more practical. A machine with real VRAM is still a better experience. The fantasy gets smaller, but the engineering gets more interesting because this is a reminder that model size is not one number. 2.8 trillion parameters sounds like a wall. 104 billion active parameters sounds like a different wall. 16 selected experts out of 896 sounds like a door. 1.56 terabytes on disk sounds like another wall. 8.24 gigabytes peak memory sounds like a miracle. 26 seconds per token sounds like the bill arriving. The useful skill is learning to read all of those numbers together. That is what most AI hype trains try to stop you doing. They give you one number and ask you to clap. Parameters, benchmarks, context length, tokens per second, RAM usage, price. But local AI is never one number, it is always a trade. This Reddit post is just a trade made painfully visible. It traded speed for memory, it traded convenience for transparency, it traded a clean user experience for a clear lesson about where the bytes live, and honestly, that is more useful than another model leaderboard. The funniest part of the whole thing is that the GPU disappears. Local AI usually turns into a GPU conversation almost immediately. How much VRAM do you have? Is 24 gigabytes enough? Can you afford a used 30, 90? Can you stack multiple cards? Should you buy a Mac Studio with unified memory? The Kimi K3 experiment steps sideways. It says, what if the limiting resource is not VRAM? What if the limiting resource is how quickly you can pull cold weights from storage? That is not as glamorous. Nobody brags about their SSD with the same energy they brag about their graphics card. But for sparse models, storage can become part of the architecture. Not storage as a place where the model waits before loading. Storage as an active participant in inference. That is a different mental model. In the normal model, disk is backstage. The show begins once everything important is loaded into memory. In this model, disk is on stage the whole time, trying not to trip over the actors. That is why the README cares about packing the trunk into one file. That is why it cares about known offsets. That is why it cares about verifying all 96 checkpoint shards. That is why a partial download is not just annoying, it can silently produce wrong tokens. When your runtime depends on streaming the right bytes at the right time, storage stops being boring. It becomes correctness. It becomes latency. It becomes cost. It becomes the difference between a clever demo and a broken one. And this is where the story points forward. If future models get bigger and sparser, then the hardware question may not only be who has the most VRAM, it may also be who has the fastest path between cold weights and active compute. It could mean better NVMe, smarter caching, runtimes that learn expert locality, or hardware designed around sparse loading. Or it could stay a fascinating dead end for interactive use, but either way, the old assumption has been dented. The assumption was if the model does not fit, it does not run. This project says, not exactly. If the model does not fit, it might run terribly, and sometimes terribly is the first step toward usefully for this channel. The question is not just whether the trick is neat, the question is whether it changes AI coding. Short term, no. If you are using AI inside your editor, speed matters too much. Coding agents are already slow when they are fast. They read files, they search repos, they run tests, they make mistakes, they wait for tools, they hit context limits, they ask for approval at the worst possible moment. Now imagine adding 26 seconds per generated token. That is not a coding assistant. That is a geological process with syntax highlighting. So nobody should watch this and think, great, I can replace my paid coding tool with Kimi K3 on 8 gigabytes of RAM. That is not the takeaway. The coding angle is lower level. Kimi K3 is an agentic coding model. Moonshot explicitly positions it for long horizon coding and terminal tool orchestration. The local experiment shows how far the open weight release can be pushed when somebody cares more about feasibility than comfort. That matters because coding agents are going to keep smashing into memory problems, not because every developer needs 2.8 trillion parameters, but because agent workloads want everything at once. They want the model, they want long context, they want tool history, they want repository files, logs, test output, multiple attempts, and memory across sessions. Every useful coding agent eventually becomes a memory management problem wearing a chat interface. That is why experiments like this are worth watching. Not because you should use this exact runtime tomorrow, because it makes the hidden constraint visible. The future of local coding agents is not just better prompts, it is scheduling, caching, routing, compression, context management, storage layout, tool orchestration, and deciding which parts of the system deserve fast memory versus which parts can be culled until needed. That is not as clickable as 2.8 trillion parameters on 8 gigabytes of RAM, but it is closer to the truth. This is the sentence that should sit on almost every local AI story possible is not practical. A model running is not the same as a model being useful. A benchmark completing is not the same as a workflow improving. A memory number dropping is not the same as your hardware problem being solved. The Kimi K3 run is impressive because it moves the boundary of possible. It is not impressive because it gives normal developers a better daily setup. That distinction matters because AI tooling is full of almost true promises. Can you run this locally? Yes. Should you? Maybe not. Can this replace a paid coding assistant? Technically, it can generate code. Practically, you probably do not want a code review that arrives tomorrow. Is 8 gigabytes enough? For RAM, apparently yes. For the whole machine, absolutely not. You still need terabytes of storage, you still need the right operating system, you still need the right CPU features, you still need patience, you still need to accept that the model is being used in a very raw form. That is not a takedown, it is just the difference between the title and the thing. And honestly, the thing is more interesting than the title because the title says Kimi K3 runs on 8 gigabytes. The thing says frontier scale open weights are forcing inference engines to become operating systems for memory. That is a much bigger idea. Less viral, more important. So what should you actually do with this information? First, do not buy hardware because of this demo. For daily local coding, a fast 30 billion class model is more useful than a giant model that takes minutes to say anything. Local AI setups should be judged by work completed, not by the largest model that technically starts. Second, stop treating parameter count as the whole story. For dense models, total size tells you a lot. For sparse MOE models, you need more numbers, total parameters, active parameters, experts per token, checkpoint size, quantization format, memory residency, storage, bandwidth, context cost, tokens per second. If a post gives you only the most exciting number, assume the boring number is hiding nearby. Third, watch the runtimes. The model releases get the attention, but the runtimes decide who can actually use them. Kimi K3 being open weight is one event. Somebody writing a tiny C99 engine that streams a model from disk is another event. Unsloth compressing huge models for local use is another event. Llama CPP adding support for new architectures is another event. The interesting future is not one magic model. It is the stack around the model getting better at cheating the hardware limit. Not cheating, as in faking results. Cheating, as in refusing to accept the obvious layout. Put this part here, stream that part later, cache these experts, quantize those weights, preserve this state, drop that overhead. That is where local AI gets better. Not in one clean jump, in 1,000 ugly little memory decisions. There's a pattern in technology where the first ridiculous version gets dismissed because it is ridiculous, and most of the time that dismissal is correct. Some ridiculous things stay ridiculous forever, but sometimes the ridiculous version is useful because it separates a hard limit from a habit. Before this demo, a reasonable person could say, Kimi K3 does not fit in 8 gigabytes, so it cannot run in 8 gigabytes. After this demo, the sentence has to be more precise. Kimi K3 can run with an 8 gigabytes working set if you're willing to stream from a giant checkpoint on fast storage and tolerate terrible latency. That sentence is much less catchy. It is also much more useful because it tells you which parts are fundamental and which parts are trade-offs. The total checkpoint size is still real. The active parameters are still real. The storage cost is still real. The speed penalty is still real. But the idea that every weight must sit in RAM at once was not fundamental. It was a design choice. That is the kind of distinction engineers care about. The first version does not have to be good to prove the choice exists. Once the choice exists, people can attack it, make the cache smarter, predict expert use, improve packing, use faster storage, move hot paths back onto accelerators, batch offline tasks, exploit repeated prompts, specialize for coding workloads. Some of those will work, some will not, but The design space is now more concrete. That is a real achievement. Not that Kimi K3 is now a practical 8 gigabytes model. It is not. The achievement is that someone turned a hardware impossibility into a software trade-off, and software trade-offs have a habit of getting less terrible over time. So yes, somebody ran Kimi K3 on 8 gigabytes of RAM, and no, that does not mean your old laptop is now a frontier AI workstation. Both statements are true. That is why the story works. The headline is outrageous enough to pull you in. The catch is brutal enough to keep it honest, and the engineering is real enough that it should not be dismissed as a gimmick. If you want a practical local coding setup today, this is not it. Use a smaller model, use enough memory, care about speed, measure the actual workflow. But if you want to understand where local AI is heading, this is one of the clearest demos of the year, because it shows the future problem in miniature. The models are getting too large to treat memory as a simple container. The interesting systems will not just load models, they will schedule them, they will stream them, they will cache them, they will decide what needs to be awake and what can stay cold. The Reddit post sounds like a magic trick. The real trick is more useful. It did not make Kimi K3 small. It made the machine honest about what part of Kimi K3 it needed now.